Section 2.1 is about functions, which are honestly a mathematician's favorite object. Almost every problem that we encounter in this course is going to involve functions in some way, even if we don't emphasize it directly. And we've seen some examples of this already in Chapter 1 when we talked about cost functions, revenue functions, and profit functions. So in order to precisely say what a function is, we need a little bit of language. So let me just remind you that a set is a collection of objects, right? For example, an example of a set would be the real number system, right? The set of all real numbers. Other examples would be intervals, right? We've talked about intervals of points on the real line. We've talked about open intervals, closed intervals, and half open intervals. Those are all examples of sets as well. And one of the things, as soon as you talk about a set, you're going to want to know which objects it contains. Or another situation is you might have a particular object and you want to know whether that object is in this set or not. So let's suppose that we use the letter capital X to represent some set, and we used the letter little x to represent some object that may or may not belong to the set. If it does belong to the set, then we use this notation to express that. And you've already seen me use this on occasion. So this just says that X belongs to, or I should say it more specifically, little x, the object, belongs to the set capital X. And if you want to say that an object is not in a set, then you'll use this notation. You notice it's the same notation, just with a line striking out the belongs to symbol. So this is how you would say that the object little x does not belong to the set capital X. Let's look at an example. A couple of examples, actually. One of each. How about? So let's say the number 4, that is an element of the open interval from 2 to 5. Remember, this is the notation you use for the interval of numbers that are strictly greater than 2 and less than 5. So 4 happens to be one of those numbers. So we can say that it belongs to that interval. On the other hand, if I were to say, write the number 7, that does not belong to the closed interval -2 to 3. So that's one example of each, right? So this is an example of saying that an element belongs to a set, and here's an example of saying that an element does not belong to a set. And we're mostly going to talk about sets of real numbers in this course, but you can have sets of anything. You can have sets of animals, sets of cars, sets of pencils, anything. There's no restriction. Any object really can belong to a set. Okay, so formally, what is a function? That's what we're finally ready to say. So a function is something, well, you have to start with a couple of sets, right? So let's say we've got two sets, x and y. And typically you'll think of x as a set of input values, and y will be a set that contains output values. That's a little bit of an oversimplification, but that's a good starting point. Okay, so we start with a notation like this, right, what you see here. I'll just got to keep remembering to use the highlighter instead. So let's look at this notation here. So this tells you that we're about to start talking about a function. And this tells you a few things about that function. First of all, its name is f. The first part that you see right here tells you that its name is f. Then after you see that full colon, then you see capital X. That tells you that its input values belong to the set X. And then afterwards the arrow, and then you see the capital Y, which tells you that its output values belong to the set Y. So the way the function works is you plug in values from X, and it will use some rule that you may or may not be aware of, quite often you are aware of it, to determine a corresponding output value. But notice this emphasis here on the phrase at most 1. Okay, so, and actually let me read the whole sentence carefully here. So it assigns to each element little x that belongs to your set capital X, it will assign it at most one element of y, and the notation we use for that corresponding output value is f of x. So, but at most one element. So in other words, if you plug in an input value, it's going to only give you one unique output value that corresponds to that input value. It's not going to give you two different possible output values. That's the big distinction. Okay, and you know what? Let's draw a picture. I think in this case, it really helps to have a picture. So this is how I like to think about functions. I think this is the simplest way to think about them. So it's a machine, right? And you've got two kind of characteristics of this machine. You have an input slot over here, and you have an output slot over here. So the idea is, and here's where the x and f of x notation comes in. Let's say I call my input value x, and I plug it into the function. So I send it into the input slot. Then f is going to do something, and you may know what it is, and you may not know what it is. But whatever the case is, f is going to do something. It's going to use its rule. That's what a function really is it's some sort of a rule to figure out what the corresponding output value is, and then it's going to send that output value back to you. Okay, so to clarify, if I use the letter x as an input value, then you'll use the notation f of x to represent the corresponding output value. Okay, just think of this picture whenever you're thinking about a function. Okay, so you've got input and output. That's really, it all boils down to that. Okay, so the notation that you see here, this is just what we just said, right? If x is an input value, then f of x is the corresponding output value. And that's, x is just a placeholder. X could be anything, right? As we're going to see in an example below, x can represent many different values. Okay, so here's some examples. Or here's one example of a function, and we're going to evaluate and simplify a whole bunch of output values. So here's the function. You see that f goes from, actually I gotta remember to use the highlighter. The way you would read this out loud is you'd say that f is a function from the real numbers to the real numbers. And you're reading it from the left to right. And let me do it this way so you can kind of see how it reads along. So f is a function from the real numbers to the real numbers. So what that means is that as input values, it's expecting a real number, but then as an output value, it's going to give you back another real number. That's how you can think about that. Okay, so how does the function work? Well, if you just look at this line, that doesn't tell you everything, right? It just tells you what type of objects you can plug in and what type of objects you can expect to get back. But now if we look over here, this is the actual rule. Remember what we said, a function is a rule? This is the rule that tells you what the function does. And if you read this carefully, and again, I'm going to do this arrow thing and show you how to interpret this. So you're saying f is the function that takes some input value, let's call it x, and gives you back the following. You take that input value x, you square it, and then you add 1, right? And then whatever the result is, that's what gets sent back as an output value. Okay, so that's how you should really interpret this. That's how you should interpret this rule. Okay, well, let's practice this. Let's actually give some concrete examples here. So how about what if we plug in the number 1? That's certainly a real number, so maybe that will work, right? So what happens if you plug in the number 1? Well, you're going to follow this rule. Take the input value, square it, and then add 1. Whatever the result is, send that back as the output value. So if we do that, we're going to get 1 squared plus 1. Well, 1 squared plus 1, that's just 1 plus 1, right? So that's going to give us 2. So there you go. That's your first output value. F of 1 is equal to 2. How about f of negative 2? Same rule, right? We're going to use the exact same rule. We're going to say negative 2 squared plus 1. So, well, negative 2 squared, negative 2 times negative 2, that's going to give you positive 4. So you got 4 plus 1, which is 5. So that tells you that f of negative 2 is equal to 5. Okay, and you know, those were whole numbers, but you can also use fractions, right? It says you can plug in real numbers. So what about something like a fraction? Okay, well, how about a half? So we get f of 1/2. So that's going to give us 1/2 squared plus 1. So what's 1/2 squared? That's going to be 1/4. A half times a half will give you 1/4. So you've got 1/4 plus 1. Now get a common denominator there, and you're going to end up getting 5/4. Okay. So just a reminder in case you've forgotten, here's what I'm actually doing. 1/4 plus 1. I'm getting a common denominator to write this as 1/4 plus 4/4, because 1 is the same as 4/4, right? And then I add up the two numerators, 1 and 4, so I get 1 plus 4, which is 5/4. So that's the logic that I'm using to simplify this here, okay? All right, so let's move on to the next one. Now here's an example of an irrational input value, right? Pi is an irrational number. So how do you, oops, I got the wrong color. How do we plug in pi? Well, same as any other number, right? F of pi, well, what does f do? It takes the input value, which in this case is pi, it squares it, and then it adds 1. So, well, what are we supposed to do from here? Well, you're not going to be able to do much better than that, right? Pi is an irrational number. It's like 3.14159 something, 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 and it just goes on forever. It never repeats. There's no pattern. It never terminates. So how are you going to do any better than what we've already done, right? Your best bet is just to leave it as a symbol, leave it as the abstract symbol pi, and just write pi squared plus 1. Now, there are certainly going to be cases where you may want to plug this into your calculator and round it off. But if it's ever just so that you don't have to use the symbol pi, that's not a good reason, right? You should have a very specific reason for wanting to get a decimal approximation, because the problem is, as soon as you use a decimal approximation, it's no longer going to be completely accurate, right? The only way to express the answer exactly is to leave it as a pi. So I'm going to add a comment here and just say this: unless you have a specific reason, don't round this off. And what I mean by that is don't plug it into your calculator and use a decimal expansion, because then it won't be exact anymore. So how about this? Unless you have a specific reason, keep this exact. In other words, leave it the way we've just written it here. Okay? Okay, so that's how you will treat that case. So if you're plugging in an irrational number. How about this one, f of y? Well, what's y? Well, we don't know, right? You have the only thing you can do at this point, if you're given this and asked to work it out, all you can really do is just assume that y must be some unknown quantity. So really just, well, go back to the rule. What does f do? It takes its input value and squares it, then adds 1. So if our input value is y, you can't do much better than just say, okay, well, y squared plus 1. Unless you know what y is, you're not going to be able to do any better than that, right? Okay, now it's going to get interesting. Well, it's already interesting. Now it's going to get more interesting. So how about f of 2y minus 1? So we've got a whole mathematical expression here being plugged in as our input value. So what do? Just treat it as your input value, right? And use brackets to help keep things organized. So we've got our input value, which is 2y minus 1. Then we're going to square it and add 1, right? So that's what it means to square it and add 1. Now, we could stop here, but sometimes you're going to want to expand this and evaluate it carefully and simplify it, and maybe you want to express it as a quadratic, which we'll talk more about those in a few sections as well. But so what you'll probably want to do is expand this. So what you're going to get here is 4y squared minus 4y plus 1 plus 1. Now, how did I get that? Let's back up a bit. Let's back up just a minute here. I'm going to add another bit of details here. Just focus on, forget about the plus 1. If I have 2y squared minus 1, that's really by definition, well, and you may think, okay, well, if I take 2y and I square it, I get 4y squared. And if I take 1 and square it, I get 1. So where did this negative 4y come from? Right, that may be a question. So you can't just simply square each of the two pieces separately. You have to realize that you're actually squaring the whole thing, right? You're squaring 2y minus 1, which means you're taking 2y minus 1 and multiplying that by itself. So you're actually going to have to FOIL this out term by term. And if you do that, you're going to have 4 terms, right? 2y times 2y, that'll be 4 squared. Then I'm going to have 2y times negative 1, which will be negative 2y. Then I'm going to have negative 1 times 2y, which is negative 2y again. And then finally, I'm going to have negative 1 times negative 1, which is positive 1. So that, once I combine my like terms, that's where the minus 4y came from. So I'm going to have 4y squared minus 4y plus 1. Okay, so that is a bit of a distraction or digression, but that is where that step is coming from. But now once we get to there, now we'll clean this up even further. The plus 1 plus 1, that could be written as plus 2. So we've got 4y squared minus 4y plus 2. Okay, so that is our final answer here. And for this one here, I guess we had y squared plus 1. It didn't really feel like we did much up here, but nonetheless, that's what your final answer for part E would be. It'd be y squared plus 1. Okay, what about f of x plus 2? Same idea, right? You're going to have the input value, x plus 2 squared plus 1, because that's how the function works. It takes its input value, squares it, then adds 1. So in a manner that's similar to what I did up here, we're going to have to expand the x plus 2 all squared, right? So what you're going to end up with, though, is x squared plus 4x plus 4. And the way you get this is by just taking this x plus 2 all squared and then doing exactly what we did up here. Okay, so I'll leave it as an exercise to you to figure out why that's the case. But then we still have this plus 1 afterwards, right? And then we can take one more step to combine the 4 and the 1, and we'll get x squared plus 4x plus 5. And then that's our final answer. But by the way, somebody might rightly ask the question, what's wrong with just leaving it like this? Or leaving this one like this? And the answer is nothing, really. And in a sense, the instructions are not totally clear, right? When we're told to evaluate and simplify, well, simplify is one of the most vague words you could ever possibly use. What we're really doing is we're expanding these expressions. We're expanding the powers and then collecting like terms. But who's to say, for example, who's to say that this is simpler than this? Or that this is simpler than this? It's kind of a subjective thing. So don't worry about getting it right all the time. But in this case, I think it makes sense to just automatically get in the habit of expanding all the terms and then expanding everything as much as possible and then combining like terms like we did here with the plus 1 and the plus 1, or here with the minus 2y and the minus 2y. So it's perfect. It's a good habit to be in. But if we had just left it like this, we wouldn't be wrong to leave it like that. Okay, one more example here. We've got f of negative 2x cubed. Okay, so by definition of f, that's going to be negative 2x cubed plus 1, which actually, if you work that out, what you're going to, oops, sorry, I forgot something, didn't I? I forgot the squared. It's going to be the square of negative 2x cubed plus 1, which what that's going to work out to is 4x to the power of 6 plus 1. And if in case you're wondering how I got that, let's back up and go through it. Okay, and then add some more details down here. How did we get negative 2x cubed squared is equal to 4x to the 6? Because that's what happened, right? This is what was equal to 4x to the 6. Well, here's the rule. What's happening here? This is actually a product of negative 2 and x cubed. Right, negative 2 and x cubed are being multiplied, and then afterwards the whole expression is being raised to the power of 2. So what's the rule for an exponent where the base, which is down here, is a product? Well, you just apply the exponent to each of the two factors. So negative 2 gets raised to the power of 2, and x cubed gets raised to the power of 2. Okay, and then once those are worked out, then they get multiplied on after, right? There's a multiplication that happens after, although you typically don't need to write that. Okay, well, negative 2 raised to the power of 2, that's negative 2 times negative 2, that's going to be positive 4. And then what about here? We've got x cubed all raised to the power of 2. Well, how does that work? If you want to raise an exponent, if you have a power, because x cubed is a power, and then you want to raise that to another exponent, you've got an exponent inside of another exponent, right? The 3 and the 2 are nested exponents. So whenever that happens, you multiply the two powers. So you got 3 as one exponent. I should say you multiply the two exponents. So we've got the cubed and the squared. The 3 and the 2 are going to multiply to give us 6. And that's how we get x to the 6. Okay. Let me just mention, and we've already talked about this, but here's a cautionary note. If I had something like, actually, let me phrase it this way. I'll start with saying what is true in general. And this is the property that we just used. If I have two real numbers, a and b, and I raise that product to the power of n, that's going to be the same as if I raise a to the power of n and b to the power of n, and then multiply the two results separately. That's the property that we really used here, with a is equal to -2, b is equal to x cubed, and then n was equal to 2. That's really what we did there. But if I were to say a plus b and raise that to the power of n, it's a common mistake that people make is they want it, it would be really nice if we could say that this is a to the n plus b to the n, right? It would make our lives so simple. I'm going to write this, but it's actually wrong. I'm going to write an equal sign, but that's actually not true. Everyone wishes that this were true. It would make life so much easier in a lot of situations. But for example, in this case, or let's go to this case actually. X plus 2 squared, if you FOIL it out, x plus 2 times x plus 2, you're going to have three different terms. You're going to get x squared plus 4x plus 4. It's not the same as just x squared plus 4. So you cannot actually do this. This is actually a false statement. So we're going to fix it now by putting a line through it. So they're not actually equal. Okay, so don't make that mistake. Okay, so that's the last example on this page. So, but yeah, there's an extra couple of reminders here. We've jumped around a bit because I wanted to remind you about a few things. So you've got a reminder on how to add fractions. Subtracting fractions works the exact same way, by the way. You've got a reminder on how to you've got a reminder on how to do FOIL, and then you've also got a reminder on how to take nested exponents.